So what I have covered so far is a very high level overview, but how does the protocol work in practice? So there is some action you need to take at the sender as well as receiver. So what are the types of actions? Let's see. So at the action at the sender, it has to decide many things. So on receiving a packet from the higher layer, should I send this packet or should I buffer it or should I discard it? If it were to receive an ACK, should I send a packet in response to this ACK? If I were to send a packet, which packet should I send? And on timeout, should I retransmit the packet? And how should I update my timeout values? So these are all the action that happens at the sender. And as a protocol designer, you have to answer these questions. Similarly, at the receiver, there are a bunch of questions. When I get a packet, should I accept this packet or should I discard this packet? If I accept this packet or not, should I generate an ACK? If I generate an ACK, what should I acknowledge in it? So let's answer these questions. So let me start out with the receiver side first. So whenever a frame or a packet with sequence number arrives, this is what the receiver does. It compares the sequence number with the last frame received. And if the sequence number is less than or equal to this, that means it has already seen the sequence number before. Or if it is greater than last acceptable frame, which in this case means that it is outside its buffer capacity, it is going to discard the frame. Now, any frame that falls in between, it is going to accept. Now, in this particular case where it has already seen this particular frame, it is going to discard. But in this case, does it make sense to send an ACK? So no matter what, it is always good to send an ACK because you are providing more feedback to the sender. As long as the sender design is handled carefully, more information doesn't hurt. And this can definitely improve performance by early detection of losses. For example, in this case, when you are sending feedback in the form of ACKs and there are holes, you can convey information about the holes. Thereby, the sender can act on that information. Of course, there are exceptions to this. For example, in some protocols like GoBackN, even whenever you discard frames, you decide not to send an ACK because it serves no purpose. Now, if you decide to send an ACK, and as I said, it is always good to send an ACK, what should the ACK contain? Now, there are two types of ACK, cumulative ACKs and selective ACKs. Cumulative ACKs are simple, but they have certain performance issues. Selective ACKs are slightly more complex. At both the receiver and the sender side, it tends to increase the complexity, but they improve the performance. So let's see what I mean by these ACKs. So in cumulative ACKs, the sequence number to ACK is always going to be the largest sequence number received, such that all frames with sequence number less than this have also been received. This LFR is the one that is set to the cumulative acknowledgement. An example helps. So for example, you are receiving frames in this particular order at the receiver. And let's say the state of the receiver is such that it already acknowledged frame 3. And let's also assume that RWS is equal to 4. So if you look at it, it acknowledged frame 3. So here is how it looks. So LFR is 3. Your window size is 4, receive window size. There, the sequence number that you are going to accept is until 7. So when frame 5 arrives, it is falling within the window, so thereby you buffer it. But the acknowledgement that you are going to send in response to this is still acknowledgement 3 because this is cumulative acknowledgement. You just send until which frame have you received in order, and that is until only 3. Now, since we didn't move LFR, LAF is also going to be the same. So now if frame 7 were to arrive, what would you ACK? What will your LFR be and what will your LAF be? That's right, you buffer frame 7 also because it is within the window, and you still send ACK 3 because there is still a hole in frame 4, and thereby LFR stays the same, LAF also stays the same. Now suppose the sender were to retransmit frame 4 on a timeout and frame 4 arrives after this. So now we have frame 4 coming. Now what will your ACK be? What will your LFR be? And what will your LAF be? So that's right, when frame 4 arrives, it's filling up this hole, so you are definitely going to accept it. And then you move your LFR all the way to frame 5, because until that point you have received in sequence, you still haven't gotten frame 6. So you're going to pause here. So your LFR becomes 5, and now that you have LFR has changed, you have to add RWS to it, which is 4, thereby LAF has become 9. And the acknowledgement that you're going to send in response to this is the value of your LFR, thereby you're going to ACK until 5. In other words, I received cumulatively all sequence numbers until 5. Now when frame 6 arrives, it's going to fill up the hole, so you're going to acknowledge all frames until frame 7, thereby your LFR becomes 7 and your LAF becomes 11. So this is how cumulative acknowledgements work at the receiver. So in selective acknowledgements, even when you receive this out of order packets, you do send your cumulative acknowledgement, but in addition to that, you also send a selective acknowledgement that specifies the sequence number of whatever packets were accepted. Again, an example helps. So we are working with the previous example, 0, 1, 2, 3, 5, 7. This is the order in which you received the packets. Now, when frame 5 arrives, you're going to acknowledge, this is the cumulative acknowledgement 3, but you're also saying I've received frame 5 as part of my window. Now, when frame 7 arrives, again the cumulative acknowledgement is 3, but you are now saying I have within my window frames 7 and 5, which is part of the selective acknowledgement. Now, when frame 4 arrives, you are going to cumulative acknowledgement 5 and you say I still have 7 in my window. And when 6 arrives, you just acknowledge 7. You have no holes anymore. So here are the sender side details. So on the sender side, whenever it receives a packet from the higher layer, it has to first sequence number it. So it will just pick the next sequence number to use and is going to give it a sequence number. Now if this sequence number that it has been assigned falls within the SWS, in other words this minus LAR is less than or equal to this, that means it's falling within the sending window, it can send the packet. Else it can buffer the packet or even inform the application so that the application will resend the packet later, in which case it doesn't have to buffer. But for now, let's assume that it is going to buffer the packet. So this is where things get very tricky from the sender side. So on receiving an ACK, whatever action you are going to do is a function of the type of ACK, and things can get very complex. For example, later when we cover TCP, you will see the lot of variants that have different actions for the same acts that come. So one thing that is common in many of these protocols is that they rely on the type of ACK, either duplicate or a selective ACK, to make some sense of packet loss, whether a packet was lost or not, and they try to trigger a retransmission. Timeout is only used as a backup mechanism. So basically timeouts tend to empty the pipe, because until you're waiting for a timeout, you're not going to send any packets, and if you're not sending the packets, you're not going to utilize the capacity of the bandwidth of the link. So you should rely on timeouts only rarely. So until I cover the TCP variants, for now we will go with a very simple version. In other words, whether you receive dupacks or selective ACKs, you use the cumulative ACK field only to advance the window. The way this works is if the sequence number in ACK is greater than LAR, you're going to set the LAR equal to the sequence number in the ACK. Remember, LAR stands for last acknowledgement received. So you're going to move the left side of the window based on the cumulative ACK. Now, as a result of this movement, your right side will also move, and as a result of this, if there is a sequence number of buffered packets that is less than or equal to this, then you are free to send them. In other words, there is space made up because some previously unacknowledged frames have been acknowledged now, and you can send some packets in place of those already acknowledged packets. I know that until you see an example, these things won't gel in your mind. We are going to see a whole lot of examples shortly. But before that, how many sequence numbers do we need as part of the sliding window protocol? See, remember that for stop and wait, 2 sequence numbers sufficed. In that case, the window size was 1. In other words, there we used one additional sequence number than the window size. Let's apply the same logic here. So if your window size is equal to 3, suppose I were to use 4 sequence numbers. In other words, I am going to use 0, 1, 2, 3, which corresponds to 4. Now, will this suffice? Now, this is going to be a function of the received window size. Let's assume that RWS is equal to 1. So I will prove that for RWS is equal to 1, this number indeed suffices. So here I have just numbered the packets P0, P1, P2, P3, P4, and if you are reusing the sequence number space, P4 has the same sequence number as P0. Now suppose the receiver is expecting P4. To show that sequence number space of 4 suffices, when it is expecting 4, P0 should not arrive. Then with this sequence number space, I am done. So if the receiver is expecting 4, naturally P3 until P3 it is successfully received. So let's look at the perspective of the sender, and here I claim that the worst case scenario will happen if P3 happens to be the last frame sent. If P3 wasn't the last frame sent, you would have moved away from P0, and thereby there is less chance of confusing the P0 with P4. In this case, if LFS was indeed equal to P3, then there is a potential for P0 to be confused with P4. So in this case, this given the fact that SWS is equal to 3, that means the sending window has to be something like this. So it has already received an acknowledgement for P0. So this has been last acknowledgement received. Since it already received an acknowledgement for 0, it would not send P0. Thereby there is no confusion of P4 with P0. But suppose RWS is not equal to 1. In this case, I am setting RWS, SWS is equal to 3. In which case, will this be sufficient? I'll prove that this won't be sufficient. So I'm going to give you an example. Suppose the sender sent 0, 1, 2. So this is what the sender sent. And the receiver received these. So the receiver is expecting 3, 0 and 1. So it kind of progressed forward. But let's assume that all the acts the receiver sent got lost. So the sender is going to retransmit 0, 1 and 2. Now the receiver is expecting the next instance of 0. But now what it got was a previous instant of 0. And this is not okay. So this definitely is not sufficient. So given this, given RWS and SWS, what is the general rule of how many sequence numbers do you need? This is something for you to work out. I will provide an answer as part of the quiz.